Hi. So this is the last second order effect in MOSFETs we'll be looking at, and it's called sub-threshold conduction. So it's almost obvious from the name itself that you know before looking at this, what do we know is that the VGS, the gate source voltage that we apply on a MOSFET, has to be greater than the VTH, that's the threshold voltage of the MOSFET, to start conduction. Now, what happens, what has been observed that we term as subthreshold conduction, is that when VGS goes below VTH, that is sub-threshold level, the current inside the channel does not reduce to a zero. ID is not zero. There is a finite current flowing even then, but it's a very weak current, it's a very small current. Even then, it is nonetheless a current. So that conduction, that current is called subthreshold conduction, and current in that case is given by this equation. It's ID equals I naught exponential VGS over, I don't know what this is called, times VT. But if you look at this, it's called, it is always greater than 1, and it's called the non-ideality factor. So, well, it's not very important as of now, but when you go into design, these considerations are very important. What happens, if you look at it, is if you look at large memory devices, devices which have memory, they have lots of transistors, and obviously we're just talking about one transistor here. And if its VGS goes below VTH and we still have a current flowing, the assumption is that there's no current, but actually there is current. That means there'll be a lot of power loss, which is not efficiency, which is not really a good efficient design. So it is generally not a desired effect in MOSFETs. And I thought I'd also mention voltage limitations on a MOSFET. We know that increasing VGS gives us a lot of current. Increasing it gives us a lot of current. But you got to be very careful, because once you increase it over a certain extent, for example, if you have very large gate to source voltage, what happens is the oxide below the gate breaks down irreversibly and your transistor is totally damaged. So there are limitations on VGS, you have to remember that. And one more thing is, if you look at a MOSFET, and this is the drain, the gate, and the source. If you have a very large VDS, what happens is the depletion region around the drain starts increasing as you increase VDS. And at one point in time, it increases more than it goes and touches the depletion layer of the of the source region. What happens is there's a direct connection just by increasing VDS between the drain and the source, which will make a large current flow from the drain to the source, which means there'll be a lot of electrons. This is current flowing, this is electrons flowing from the source to the drain. Nonetheless, there is conduction between the source and the drain, and this large conduction is not desired again, because well, it's not desired, that's all. So yeah, so we have to take care of VDS, the limitations on VDS and VGS. So these are the second order effects I wanted to talk to you about, and also on voltage limitations. Once we're done with these, I mean, now that we're done with these, we can go ahead and look at amplifier designs. That'll be following this lecture. And hope to see you there. Thank you so much.